All right, so welcome back, everyone. So as I promised, we are going to do a mix of physics lessons and a mix of gameplay. Played a little bit, and I introduced a little bit of a cool animation and drawing of water. Now, what I want to show you, or what I'm going to be using, is going to be my own tablet. I have just some lecture notes I've prepared for today because, sometimes I wing things, but sometimes... Is there a bunny in here? Do I smell a bunny? But sometimes I do need a little bit of, what's the word? A little bit of guidance and make sure I don't sidetrack too much when I talk about these things. Play a little bit of background music as well. Hello, Nexus. Welcome in, welcome in. So, let me pull up my lecture notes. I have my tablet upside down. We have a little bit of Expedition 33 in the background as well. So that is on kinetic theory of gases. There we go. Cohesive and adhesive forces. So something that you might have noticed when we're playing the game, and maybe you've noticed in life in general, is that water doesn't behave as flat as we think it does sometimes. So that's exactly what I want to talk about. And there's certain creatures in the world, in the universe, that can walk on water. I know. You thought it was just... I was going to say it was Jesus Christ who did that, but I don't remember. I think I got my lore wrong. Did Jesus walk on water? Anybody know the lore? Can anyone confirm or deny the rumors I'm spreading? Is that good? Yes. You can see my 3D printer and my whiteboard. Excellent. Excellent. Yes, you are correct. Okay. From water into wine, that's right. Let me clean this off. This is a bit of spoilers about what's to come later today. Let me know if you can't hear me. I know obviously I'm going to be far away from the mic, but let me know if you can't hear me at some point. Yeah. Close the door. Sorry, I'm gonna have... Thank you! Alrighty then, ladies and gentlemen, here we go. Alright, so again, just in case you're wondering, there you go. Yeah, no, sorry, I hit the thingy-mabobby. Apologies. Don't worry if you missed the screenshots of the board if you wanted to have it for homework. We will be covering it later on stream. Yes, time to learn, Jewel. You're more than welcome in here. So the first thing to cover, or the first thing I want to mention, is surface tension. It's something that we mention about water, and have you ever heard the notion of the fact that if you jump off a cliff and hit your body off the water, it's the same thing as jumping onto concrete, right? You think, oh, that's a bit silly. And there's a reason why. Divers dive the way they do, where they put their hands together over their head and they point their fingers into the water. The idea behind it is that their fingers, because they're in a sharper point, actually quite literally break the surface tension of water. So if I put a little drop of water, aim the mic a little bit closer to me. If I push like a little pipette of water, a droplet, on a surface, it looks like that. It looks like a semicircle because of this weird phenomenon that we do refer to. It's better to break their fingers than their back. Well, I suppose that's one way of looking at it. That's one way of looking at it. Another way of kind of looking at what surface tension is that if we have a container of water, let me think about this. Do you know needles, sewing needles? If you've ever seen a sewing needle, you know that it's super, super skinny and thin. Now remember when we studied density of materials, if you had a piece of wood versus a piece of metal, a metal would sink while a piece of wood would float because its density is less than that of water, right? Even if a needle is made out of a metal that is more dense than water, the condition is that it has to actually break the surface tension of water initially. So it doesn't affect its density. We haven't changed the density. The material is still the same. So let's say we have a block of metal here. So this is H2O. This is metal. And just instead of using a metal material or, a specific metal description, I'm just kind of fluffing up the statement because I actually don't know what metal needle is made out of. If anyone knows, any knowledgeable people in the chat know what metal a sewing needle is made out of? It's steel. Is it steel? Stainless steel. Cool. So if we don't want, just an arbitrary word, we can replace that and say metal. Say steel instead. So a block of steel will sink, absolutely. But if you have a super, super thin needle, tiniest thing, it will actually float on the surface of the water because it doesn't break that surface tension. So let's look into what's actually happening. Let's zoom in on this picture. Zoom in. So water, the chemical symbol is H2O, made of hydrogens and oxygens. We zoom in, we have on the surface a bunch of water particles, and we have water particles evenly distributed around. Okay, so this is the surface, while this is the rest of the water of the particles. So what actually ends up happening is, there's actually different ways of teaching this. You can teach this in a chemistry way, in a physics way, in a conceptual way. There's all these different things. If you look from the perspective of each molecule, actually, I'll redraw it a little bit. Sorry, I'm just going to redraw it ever so slightly differently. A bit more structured. I'd like to highlight, not drawn to scale. If you look at each molecule inside the water, it has a force field upwards, to the side, and to the other side. It has a force in all directions that it feels, right? If you look at every single molecule, they feel the exact same way as any other molecule beside it, or in the bottom of it, or below it, or in any other given direction. Except which one, chat? Which one does not feel the equal forces in all directions? The surface layer, right? The surface layer doesn't have that upward connection to another water molecule above. And so it has this, there's two things happening. First of all, there's this chemical bond issue happening that it doesn't have, like, let's say, you can imagine that an oxygen molecule has 4 hands, right? It's holding hands up atop, up below, to the right, to the left, okay? So it's a good structure, we're holding hands together, we're all happy. But the problem is with the top layer of oxygen, it doesn't have a hand to hold. So where does it go? It gives an extra bond or an extra charge or an extra attraction to either right or left. So as you can see, I've actually drawn it already, that the surface layer of the water molecules are actually quite literally tighter together. This is the premise or the idea of surface tension. Well, one of them, all right? There's another one I want to talk about. Hi, welcome in, Clem, Jewel, everyone, welcome in. Hello, Panda. Hope you guys are keeping well. Welcome in, welcome in. So these guys have even bodies, and so they're evenly distributed, but the water molecules on the surface do not have upward bodies to connect with, and so that they push through each other, and there's a tighter attraction there. Now, you might also kind of start probing with the chemistry. It's like, well, what is this attraction? This is hydrogen bonds. If there's anyone here who studied chemistry or remembers chemistry, I apologize if I'm re-traumatizing you. But I'm not going to go into hydrogen bonds too much. Just know that between different hydrogens, because H2O is O and two hydrogens sticking out, hydrogen bonds is one of the strongest bonds that does exist, and they do keep things intact. I'm an IT student, but I'm here to learn new things. That is the type of people that are welcome here. We don't care what your background is. We don't care about your education, as long as you're here to learn. And if you want to teach me a thing or two, you're more than welcome, as long as you're not sassy about it. The only sass that's allowed is from me. Sorry, I'm just grabbing a fan. I forget that when I'm up and standing and moving, it gets hot in here. It's getting hot in here. So take off. Don't take off your coat. No. I was never interested in physics, but yet this game. Yeah, the game is really, really good. What was I going to say? I'm hoping it'll be really, really interesting. Now, before I get distracted and stay on the topic, we have surface tension, right? We have surface going up, down, right, left, but on the surface of water, all the molecules are really, really jam-packed together. And another thing to talk about here as well is that we have forces, you guys kind of highlighted. There's forces going downwards, left, right, up, but on the top layer, there is a net surface going down. Does that make sense? So, the reason I bring this up is there's a very unique shape as to why water is the shape that it is. Aussie here. Well, in Australia, it's the opposite way, isn't it? Gravity is still the same, I promise. But because of that, because of the tightly jam-packed molecules on the surface layer of the water, there's an inward first downwards. And that is why droplets tend to be spherical in shape. Now, you can also imagine as to a little bit of logic as to why raindrops, when they're falling, they're like this. This is also a mix of like gravity, them falling, air resistance, all of that. But generally speaking, droplets will be in a circular shape. That is why they do it. First of all, because of the net force downwards, and because of that outer layer on the outside, the surface tension, the molecules want to bring them together like that. So, if we want to put a bit of maths to the logic that we've just put in here. Oh, sorry, the music is Expedition 33. Yes, it's one of my favorite games that I play this year. I hope it wins Game of the Year. It's really, really good. For the soundtrack alone, if anything. So, another kind of logical thing, I have actually a little note here, is the sphere is the best shape to minimize surface area for a given volume. So I'm going to put that up on the board. Minimize And I kind of mentioned this before a little bit, and when we talk about solar panels and why solar panels are a certain shape that they are, or why do we like circles? Why are we as a human race obsessed with spheres and circles? I don't know if you've noticed in life, it feels like everything is a sphere, everything is a circle, and you're not sure what everything else is in between. Why do we want everything to be a sphere or circle? But one of the cool things in physics or in pure mathematics is that it is the minimum shape, right? It is the minimum shape to minimize the surface area for a given volume. So let's say I have a meter cubed of something, let's say a liquid. If I wanted to have the least amount of surface area, i.e. the area of the object on the outside, the best object in the universe is a sphere. maybe you might be wondering why everything is spherical and things like that. Although it's not perfect, especially in like galaxy conversations or planet formations and stuff like that. I don't know if it necessarily plays a direct role, but it is just an aspect of a lot of little things. There is a brain thought as to why things tend to be spherical. That's just got to do with gravity and the way it acts. You can kind of imagine that it is kind of like this, the surface tension acting inwards always, and gravity is the opposite. It ends in, not opposite, but same thing in the same direction. It acts inwards, and that is why things do tend to be in spherical shapes, or a little bit squashed spherical shapes. Now, to do a bit of mathematics on the subject, let's talk about surface tension. The letter that we give surface tension is gamma. Okay, we're probably familiar about it in common kind of tongue. We talk about it when we talk about gamma radiation. You've heard of it before. Not to be confused with gamma radiation, okay? We just tend to reuse Greek letters where we can, especially when they're in different fields. So no one, when they're talking about surface tension or like tension or liquids or things like that, is going to confuse this with gamma radiation. They're just going to assume that we're talking about surface tension. And it is defined as force over length. Maybe you can extract the units from that. Remember what our units for force are? Force is equal to ma, mass times acceleration. We can talk about it in kilograms, meters per second squared if we wanted to. Or we also have Newton, right? So Newton is for force. Length is a length. Good job, Tofu. Length is in meters. So the unit for surface tension is Newton per. What is the force that is experienced per unit length? That is what we define surface tension as. Now, before I get to capillary action, I am going to kind of explain a little bit as to how do we measure surface tension, because there is like, what's the idea? There is ideologies out there of, not ideology, sorry. There are measurements, right? If you look up on Wikipedia or something like that, you'll say, what is the surface tension of water? What is the surface tension of oil? If you look up these things, you'll see that it's a given value, and you might be wondering, well, how do you measure it? So this is actually how they measure it IRL. They get a basin and fill it up with whatever liquid we're studying. Let's say, in this case, water. Google thought I asked it a question. Okay? And what they do is... No, stop. What they do is they have a ring, like a metal ring, on the surface of the water, like this. Okay? There's a 3D look on a 2D drawing. Apologies. It's a circle wire, okay? And the circle wire is suspended by a little measurement that can measure force first, usually like a little hooks kind of demo. And it measures the force as you pull it up. Surface tension will that's terrible grammar I wrote. So as you pull this ring up and up and up, you're going to get an increase in the angle. So if you zoom in, super zoom in on the wire, right? Let's say this is the slant you get from the wire. Can I see that actually? You might not be seeing it. Let me clean the board really quickly so that we can see it properly. Okay. Can swimmers take this knowledge to improve their craft in diving? I think swimmers know a lot more about this than I do in terms of experience. Vibes and feels are probably more important than actual physics, mathematics for divers out there. Don't tell them I said that though. They should still be studying physics. Everyone should be studying physics. So if we zoom in on the wire here, so imagine this is the wire. I've done a cross-section cutoff, and the water on the surface, right, normally would be here. But because there's surface tension, I'm going to stick to like that, okay? And so what you do is you lift and lift and lift this ring. There's a force upwards. The angle is going to keep increasing, right? It's going to get steeper and steeper and steeper until what? What happens? As this angle gets steeper and steeper and steeper, it eventually snaps. In that moment where the surface tension breaks, exactly, when the surface tension breaks, that force is the surface tension measurement. That is F. Now you might wonder, well, how do you get the length? It's the length of the wire, 2 pi r. Technically it's twice because there's one on the inside, one on the outside, but that's a small thing. But that is how you measure those two things. You want to measure what the surface tension of a liquid is. Now, that is a little bit about surface tension. A small note, or a really interesting point about molecules, and generally speaking, is that if you increase the temperature of your liquid, the surface tension decreases. So if in our colony, in Oxygen Not Included, in Tofu's Minions, right? If we keep increasing the temperature bit by bit by bit, the colony is going to... Really what should be happening is that the meniscus, the curviness of the water should be decreasing. It can't hold that surface tension as much as it could in colder. That's generally speaking how these little bits and bobs work. The F is perpendicular to the L is the thickness of the L imaginary. Yes, it is 2 pi, because remember 2 pi r is the circumference of the circle, right? I'm right? That is the formula of, I'm not crazy, am I? Am I? I hope I'm not. But you have the inner circle and then you have the outer circle. So the thickness will affect that. But I suppose it's so super thin that hopefully it's the same, or it's not an issue. Now, that is the discussion a little bit about surface tension. Another thing that we turn to refer to it is, I have a little note here because I always get these words mixed up. No, I'm not typing. Can I please look at my notes? Here we go. This is the word I'm looking for. When we talk about surface tension, another word that we tend to use is cohesion. This is the cohesive forces of water. Cohesion. Did I spell it right? Cohesion. I think I did. Now, why might I say that term? What does cohesion mean? Well, it talks about the attractive forces, specifically with water itself. It's how much water likes water. Okay? That's the idea behind cohesive forces. Water loves itself. It's a little bit, what's the word? I was not going to use self-entitled. What's the word I'm looking for? Self-absorbed? Yeah. Water is a little bit self-absorbed. That's funny. And it loves to stick to itself. And that is why it forms this droplet. That is why it sticks together. Water is quite a sticky substance in itself. But another thing that can happen as well is an adhesive force. This is sometimes what we talk about as capillary action. Have you heard about capillary action? We talk about capillary action quite often in other fields. For example, in biology, it's how our blood vessels work. It's how, exactly, Kate, it's how plants move water from the roots all the way up to the tops of the trees. Exactly. So adhesion is the power overlord. Adhesion is the attraction between different types of molecules and atoms. So something really weird happens. Number one, water likes itself. It loves itself. It's self-obsessed, right? But another thing is it likes other things too. And so when you look and zoom in at a test tube in the lab, you'll notice water do a very interesting thing. It's not like this. No. It's like this. Water starts to stick to the walls of the test tube, and there's that little curve. So remember in the game we saw it kind of sticking to the outside parts, or the different layers or the different outskirts of the material that it was in. Oxygen Not Included did get that little bit part about water correct, where it does tend to stick to those little things. Now I did have like a little demo with capillary action to show you the different heights and stuff, but unfortunately it didn't work. Now what's really interesting, and I did bring a little test tube and oil. I don't know if we'll see it properly though, but something interesting that happens is that we're talking about water all the time. We're talking about water all the time when there's other liquids, right? And there's another liquid that's really, really cool for all these demos to talk about that is the opposite to water. One of those things is oil. Oil is super self-absorbed. Hi, Jimmy, welcome in. If I had a test tube, again, but this time oil, get this orange marker here. It actually forms a bulge in the opposite direction. It goes upwards because oil it's so phobic, this proper word we do use in science, to the material of the test tube, and it pushes itself away. It sticks together, it still likes itself, and this has all got to do with hydrogen bonding, by the way, still. It likes itself, it still wants to stick, but it doesn't like the walls, and it stays the F away from it as much as possible, and that is why it bulges upwards. Now, water likes itself still. It does. It's the same as oil. It likes itself, but it also likes other materials as well. And that's why it sticks to water and sticks to itself. Really cool outcome in these aspects is the people up in the International Space Station. How do they wash their face? How do they... Have you ever seen how they've cleaned themselves? Any images or videos about it? When they get the water out, it kind of floats in, stuck together, first of all, because of surface tension, because of cohesive forces. And then when they put it to their face, it sticks to their face because of adhesive forces. So there's two things. Cohesive and adhesive. Water sticks to itself and water sticks to the astronaut's face. So you can use both in that case. Water sticks to everything. Exactly. Now, I did have a demo set up to show you this, but unfortunately I couldn't do it. Because it didn't work. It was a bad experimental setup. But the idea behind the experiment that we usually use is that we get like a little tube like this, right? We have a big tube, a thinner tube, an even thinner tube, and an even thinner tube. So I'm just going to show you the results of this experiment. Is that if you fill up this bad boy with water, this is sometimes a demo that you use in physics school. You fill this all up with water, you'll notice that the capillary action will go upwards more and more and more and more the thinner the tube is. And we actually can put a mathematical equation to this. What height will a material actually travel up a tube depending on how skinny it is? And the equation is H is equal to 2. We know what the number 2 is. Gamma, that's the surface tension. We talked about it. It's force over area. We mentioned this before. Cos theta, the angle, the curviness angle, times rho, the density of the liquid, G, the gravity, because gravity is acting downwards against it. So it does depend on what planet you're on. times r, the radius of your tube. Because if you look downwards on a tube, it's just a circle. So it's r. We can put a mathematical equation to calculating how much liquids will go up tubes. And this is how water gets transported to plants, how capillary action works in our blood vessels. I'm actually not sure about that one. I just assume that's true because we call our blood vessels capillaries, the really thin ones. I just put 2 and 2 together. If anyone can confirm or deny the rumors I'm spreading, happy for people to chime in there. Water can be sticky on a macro scale as well. Float planes have a very hard time taking off from a flat calm surface. Oh, cool. A little bit of wave action makes lifting off much easier. Cool. In terms of another example of surface tension is that what are they called? Water skaters? Water skirters? There's a bug that goes whoosh, whoosh, whoosh on water. You know the bugs I'm on about that come out during the summer on the ponds? You see them going ziggity zaggity. You studied this in grade 11. That's unusual. We don't usually cover... There's too much stuff to cover in physics to be covering this. Water boatmen. Oh, I've never heard of them called water boatmen before. I think I've heard of water striders. But I've never called them water boatmen. That's interesting. There's some pressure force behind the blood capillaries from the heart. That's true. Our heart is a pump, quite literally like a water pump. And you, hello Envy. Welcome in everyone. Loads of new people. Jet ski, are they called jet ski? Yeah, you guys are more than welcome here. I know we're on the front page, so there might be a few people jumping in. You guys are more than welcome here. I'm Tiny Toxic Tofu. If you want to get in my good graces, you can refer to me as Dr. Toxic Tofu. We do have a bit of a evil lab going on here. You don't see much of my lab background, but we have more cool stuff in the back. I teach physics and science. And in my spare time, I play games. So today's feature is really cool. We're playing a game called Oxygen Not Included. And I have 3 lessons planned around the game. So we're going to keep switching between the game, a lesson, game, lesson. And the game has really beautiful artwork that is inspired by real physics. And one of the things is it does adhesion and cohesive forces in the game really well. So I zoomed in on it, showed a little bit of it, and I did a lesson on surface tension and capillary action. So that is one of my lessons complete. The second lesson, I'm not going to spoil what it's going to be in about an hour or an hour and a half, but it's still physics. But it's going to involve big potatoes. We have potatoes. I know, very Irish stream, me streaming with, you know, potatoes on stream. But it is going to be a very important lesson if you're interested in learning more. There's also a lot of more chemistry involved in this. Like I said, the hydrogen bonding stuff, even though you actually do study a little bit of in physics as well, there is a lot of different layers to learning this. So as you guys notice, we hit on physics, we hit on chemistry, we hit on biology. And you know why? Because I'm a pretentious snob and I always tell everyone everything is physics. So you're all physicists in my heart. Everyone is a physicist somewhere deep inside.